So if we're talking about the number of heads when we flip these 3 coins, okay, do you guys remember, what kind of variable is that if we're talking about number of heads? Categorical or quantitative? Quantitative, because our result is a number. Okay, we also once we had quantitative variables, we had discrete and continuous variables. Do you guys remember the difference between continuous and discrete? Your shoe size is discrete. The amount of inches in your foot is continuous. Because you can have 7.6325 whatever inches on your foot. But your shoe size is a 7 or a 7.5. There's nothing in between. You guys remember? Is this good? So when we look at this particular variable, the number of heads when we flip these 3 coins, is that continuous or discrete?
Discrete.
It is discrete. I know that because I can't have 2.5 heads. I either have 2 heads or I have 3 heads, but there exists an in-between space that I cannot equal. Okay? Cool. All right. So from this, we can make this probability distribution. What are all my possible outcomes? Well, the smallest one seems to be, what, 0? And then 1, and then 2, and then 3. Okay, you guys. Of the 0, the 1, the 2, the 3, are they all equally likely? Why? Some happen more than others. There's only one way to get all 3 coins to be heads. There's 3 ways to get all 2 heads and a tails. Is this making sense? Okay, so this would be 1 out of 8, 3 out of 8, 3 out of 8, 1 out of 8. In terms of those probabilities. And we can, in fact, make a graph of each of these probabilities. And that graph is going to look awfully familiar. What does this look like? I'm going to struggle with normal. Normal typically describes continuous variables. But are you guys with me that we just drew a histogram? Is it okay? And so there's like a very subtle but important thing I kind of want us to discuss here, okay? And that is, like in the past when we drew histograms, we gathered a sample, and it was a histogram of a sample. We don't have a sample here. This is more of a theoretical distribution than it is the distribution of a sample itself. Is this okay? But other than that, we have the values, and when we think about this probability, and we kind of talked about this last unit, we're going to talk about it a whole lot more this unit, this half of this unit, okay, is probabilities are how frequently something should happen in a large number of trials. When we drew histograms before, what was our label on this axis? The vertical axis, what did we say it was? It was the frequency. Are you guys with me that probability and frequency go together as long as we have a large number of trials? Everybody good? All right. Now, the other thing we did with histograms is we described what we saw. What were the three things we need to describe? Shape, center, and spread. Okay, what's the shape? Again, discrete versus continuous. I'm not comfortable calling this normal. I would be comfortable calling it unimodal and symmetric. What about the center? Ooh, I don't agree with that. Because remember, the average would be, when we're looking at this, the average we'd be looking for is the average number of heads.
Yeah. 3/8.
This axis is my number of heads, yeah?
1.5.
Is everybody good with the average being 1.5? Is that saying that we're going to get 1.5? No, it's saying that if we took the average of all of the possible times we did this, the average would be 1.5 heads. All right. What about spread? What do you guys want to use here? At least for right now. Well, so remember that the range is not two numbers. It's a distance between, right? So we're trying to say, well, it's essentially the distance between these two values. So the range is approximately 3. It's not 0 to 3, it's just 3. It's how much of the number line does my graph take up? So I guess the connection I'm really hoping that we are starting to make is that when you have one of these random variables where we have numerical values with different probabilities, what we actually have is a distribution. And if we have a distribution, we have a shape, a center, and a spread. Just like we did before. Just like we would with a real sample of data. You can have all of those things on this theoretical set of data. Good so far? Okay. I'll let you guys go ahead and read this real quick. All right. What do you guys think about this game? Does it sound fun? Maybe? All right. So we had 3 possible outcomes, yes? What's the first outcome? We spin a white. What's the probability I spin white?
1 out of 4.
1 out of 4. Or if you guys want to call that 0.25, that's cool. What about gray?
Also 1 out of 4.
Blue would be 0.5. Yeah. Okay. Now, when it comes to this idea of this random variable is how we take the spinner and apply numeric values to the spinner. So right now, you guys, if we let G be the player's gain, here's what we mean by that. At the end, how much money have you made? Cool? So let's go ahead, and are you guys with me that when you spin a white, there's a number we could associate with spinning white. And what is it? You're up $1. You paid $1 to play, right? Okay? And you've won, so you're going to get your $1 back plus another $1. So white equates to a +1. So we have the probability from the spinner, and then we have the random variable. Typically, we use capital letters to describe random variables. Okay, so I'm using G to stand for a player's gain. Okay, what if you land on gray? What's your gain? You get your money back, right? So you're not walking away with less or more. And that's going to happen 25% of the time. And if you spin a blue? -1, because you're walking away with less money than you started. What's the probability of that? 0.5. Cool. Cool, cool. Now, what if we flip perspectives? Right? We could define a completely different random variable. This time, the random variable is Miss Meister's gain instead of the player's gain. Right? So, if it lands on white, what's going to happen from my perspective instead of from your perspective? I'm going to lose $1. If it lands on gray, I'm going to break even. If it lands on blue, I'm going to take $1 home. Everybody good? So, these are discrete random variables. Random being that it's a chance process. Okay? Why are these discrete? Say that again? It's an exact number. On any given turn, you're either going to get -1, 0, or $1. Yeah? Okay? Are these legitimate probability distributions? Is it every possible outcome? Yeah, and how do we know?
It all adds up to 1.
Am I going to make money? If I were to play this a large number of times, am I going to make money? Are you going to lose money if you play it a large number of times? Because you know what I could say? The probability that I make money is 50%. And the probability that I don't make money is 50%. So is this game fair? I'm as likely to make money as I am not to make money.
Difference between making money and
There's a huge difference, right? Hey, if you could change one payout to make this so that it's fair, what would you do?
Like the gray, white, or
One numerical value. So in other words, I'm still going to have gain $1, break even, and lose $1. Is everybody with me? Sorry. You guys make money. There's going to be a section where you don't make any money. And then there's going to be a section for when I make money. Do you guys see what I'm saying? So how could I make this more fair to you guys? So if I handed you guys so that your gain would be $2, you would think this is more fair. Do you guys agree with that? Would this be a fair game? Even though it's your equal likelihood of making money and losing money, right? Or equal likelihood of making money and not making money. Making that payout, if you earned $2 here, you would feel better about the game. Yes? No? Do you think it would be fair at that point? Would you be more willing to play the game? Okay. Reasoning is perfect. Or that you're correct, that it would be a totally fair game if instead I gave you guys $2 back instead of $1 back. Or you know what I'm saying, a gain of $2. Now we just got to figure out a mathematical reason why.
Double it, you lose money versus make money. So if you double the amount, you win, even though the probability doesn't change.
Okay.
Your odds of winning are still low, but since your winnings are higher, it kind of cancels out.
Kind of, yeah. Let's play this through, okay? 1, 2, 3. The 4 of you are going to play this game. You with me? These 4. Macy, you're going to spin a white. Yeah? So what happened to Meister if we use the $2? That would be Meister loses $2, yeah? Icarus is then going to spin a gray. So when that happens, Meister stays even. And then, sorry, you two. You're both going to spin a blue. Everybody with me? And that would be Meister gains $1. Times 2. It's going to happen twice. So overall, did Miss Meister make any money? Lost 2, got 2. Yeah? And if we did this for a large number of trials, this would happen a lot. Yeah? Okay. What we just found was something called the expected value. I'm going to give you a formal definition of it now. Okay? But the idea is, if I still average out to 0, I would want the average or my expected value to equal 0 for a game to be a fair game. So it kind of goes like this. All right. The mean of any random variable is the sum, that's the fancy sum, this formula is on your formula sheet, by the way, of the possible times its probability. That's a fancy way of saying. We use sub-i's because we have 3 different options here, okay? So if I would kind of do that distribution G, and I'm going to go back to the initial one. We had a 1, which was 0.25, a 0, which was 0.25, and a negative 1 that was 0.5. here's what I mean by this. And I think this will make sense when we do it. If I consider my outcomes, outcome 1, outcome 2, outcome 3, and those are my 3 possible outcomes, using this formula would be I take the outcome times its probability plus the outcome times its probability plus the other outcome times its probability. Outcome 1 times P1. So this is X1 times P1. This is X2 times P2. This is X3 times P3. Each outcome times its probability. Another way of saying this, we would expect you to win 1, 25% of the time, 0, 25% of the time, -1, 50% of the time. We're just taking each outcome times its probability, adding it together. So if I want to find the mean of G, this is fancy notation, okay? But that curly Q mu we've kind of talked about as a mean, okay? I would do 1 times 0.25 plus 0 times 0.25 plus -1 times 0.5. And you guys, what do I get when I add all those things together?
-0.25.
So, remember we said we're all going to play this game, right? Now we let everybody play. On average, how much money will you guys get per game? You're going to lose 25%. Or 25 cents per game. So, let's talk about another fancy word called the variance. Variance is just the square of the standard deviation. And essentially the way we find it is we take big picture. Let's step away from this for just a sec. What does standard deviation mean? What is like the overall understanding? What's your understanding what standard deviation is?
The distance, however many distances from the mean.
It's for each observation that we have, the average distance each observation is from the actual mean itself. And how do I find the difference or the distance between two numbers? I subtract them. Everybody with me so far? Okay, so this 1 is one of my observations, correct? And the mean we just figured out was -25 cents. How far away is gaining $1 away? How far away is that $1 from the -25 cents? 125, yeah? Okay, so what you're going to do is you're doing the observation minus the mean. Now, those distances, are they all equally represented? In other words, do we have as many 1s as we do -1s? %25 of my observations are going to be a 1. 50% of my observations are going to be a -1. So are they equally represented? No. So what we do to accommodate for the fact that they're not equally represented is we multiply by the probability. And there's something else we do. For this distance, y'all, this is 1.25. If I subtract this one, I get negative 0.75. Can I have a distance that's negative? No. So here's what we do. Let me get those out of the way so that it doesn't look like a fraction. For every one of those distances, we square them first to make them positive.
Why'd you write a 2 on the little, like, symbol?
Say that, like here,
Yeah.
the variance is the square of the standard deviation. Like the way you go back and forth, this is going to come up a lot. So it's, in general, the word variance, which we haven't used much because your calculator's done all these calculations for you, okay, is going to come in big on this, on Friday in particular. You'll see it in what we're doing on Friday. Okay, and the variance of a data set is the standard deviation. If you take the number of that standard deviation, you square it. So the variance is just the standard deviation squared. Period. That's the name. That's what variance means. Do you know you're typing that in for me? What'd you get?
0.6875.
And that was for the sigma squared, right?
Yeah.
Okay. Right, so you guys, how would I figure out the standard deviation from there? We have sigma squared g is this 0.6875. That means sigma, or the standard deviation, is the square root of that 0.6875. Which I'm assuming is like 0.8283. Biscuit, the look on your face is like not one of confidence.
Not yet.
Okay.
So if everything was equally represented, we wouldn't.
You wouldn't bother with all of this. Because you could just find the mean and the standard deviation of the numbers. Okay. Let's go ahead and do this again. We're going to do it with this data set real quick, okay? All right. So we're saying X is the number of cars sold. This is a car dealership, and we're just talking about, I think this exam, like seeing it worked through another time will help you see how to do this a little bit better. Okay? So on any given Friday morning, this dealership's 30% of the time they're not going to sell any cars. 40% of the time they sell one car, et cetera, et cetera. Everybody good? Okay, so if I want to find the mean of how many cars they actually sell, I'm going to say 0 times 0.3 plus 1 times 0.4 plus 2 times 0.2 plus 3 times 0.1. That gets me my mean. Are we comfortable? $1.1? Is that right? Are we feeling good so far? Okay, next. The standard deviation is going to equal, we're going to take the square root of a bit of a long thing, okay? You're going to take, how far away is this first possible outcome from the mean, and then times its probability. So I kind of here, just to kind of help you guys see it, everything that's underlined in purple right now, those are just my possible outcomes. 0, 1, 2, 3, and it's just those outcomes distance from the mean. And we square it so that positives and that, so that those distances kind of become positive. Okay? And everything underlined in orange are the probabilities associated with those outcomes. Anyone got it? 0.94. Okay. Tomorrow I have that same monthly meeting that I always have. Okay. What I'm going to do is I'm going to start with I'm going to make a recording for you guys for tomorrow's class. The very first thing I'm going to show you is how the calculator calculates this for you. Like how you can find this in your calculator. Okay, to start today, guys, I'm just going to start where we left off yesterday. I know that yesterday we kind of talked about these formulas to calculate the mean and the standard deviation of this random variable if we were going to do this by hand. Today I'm going to show you the shortcuts in the calculator. Before I do that, I do want to say that if on, say, the AP exam, you were asked to make these calculations of the mean and the standard deviation, you would, in fact, be expected to show this work. So, that being said, the formulas, for instance, the formula for the mean is on your formula sheet where it is the sum of xi pi. That essentially means the sum is summation, so that's why we're adding each of these. The outcome times its probability. The outcome times its probability. Also on said formula sheet, there's a formula for the standard deviation. And the formula for that standard deviation is equal to the square root of the sum of xi minus the mean times the probability. In other words, xi minus the mean that we calculated from above times the probability. So the 0 and the 0.3, but so all of these have a minus 1.1 squared. And there's a squared on it here. So like the formulas are kind of given to you, and you would be expected to show some of the work on the AP exam. But I am going to show you a calculator shortcut to kind of make it go a little bit quicker. And I will say this, it is very, very rare that the College Board asks you to calculate the standard deviation. They usually give it to you. It's not never that you have to calculate it by hand. It should not shock you at all to have to do this process, but to do the big long square root is less likely. Okay? So how do I do this? So you'll notice the first thing I did is I hit stat, I hit edit, and I went ahead and put my outcomes in L1 and each outcome's probability in L2. Okay, and essentially we're trying to find the mean and the standard deviation. So what you can do, in the past when we had to do mean and standard deviation, we hit stat, we arrowed over to calc, and we chose this first option of one variable stats. Instead of doing the one, we're still going to do those one variable stats. Before, we left this frequency list blank. But when you think about probabilities are really just how frequently certain outcomes can occur. So you can tell it to find the mean and the standard deviation of L1 when those outcomes happen with the frequency of the probabilities you put in L2. And so I can go in and do that this way. You can see that we have the exact same 1.1 for our mean. We have 0.94 times for the standard deviation. We kind of talked about that this isn't the probabilities of an actual sample, so the calculator won't even give us S because it knows that this is a theoretical sample, so we're kind of describing a population. Okay, so that's how you find this stuff in the calculator. And put the calculator away. And let's kind of move forward to the next. How do I stop this video? Okay, try this. You guys, we're just going to keep going. Okay, automatically pause when I